Assalamualaikum and good day. My name is Muhammad Aidil Aswad bin TUAH and I am under Supervisor of Associate Professor IRTS Dr. SOLEHUDDIN SHUIB. Today, I am presenting my final year project under the title Design for Additive Manufacturing for High Flexion Knee Implant. Presentation outline for this project. In this presentation, I will cover the introduction, objective of this project, scope of work, methodology, findings or result, and lastly is conclusion for this project. Knee implant is one of medical implant to replace broken knee. This project is to provide an alternative medical device for individuals who experience knee problems. Medical implant is the device or tissue that are placed into the body surface. Medical implant is to replace lost part of the body. Implant can be put in or removed permanently when no longer necessary. Total knee replacement (TKR) is one of the greatest treatment or final option for patients who are suffering knee problem. First knee substitution operation was carried out in 1968. Since then, innovation and improvement in surgical material, design and technique in TKR have greatly improved. Total knee replacement in all medicine are among the most successful. According to the Agency for Healthcare Research and Quality, in 2017, more than 754,000 knee replacements were carried out in United States. And in Malaysia, the first TKR replacement operation was performed in 1970. Knee have three bones that join each other, which is femur, tibia, and patella, while tendons are the connection that connect the knee bone to the muscle. So the function of it is to move the knee joint. The knee can be injured in many ways, such as result of a road accident or sometimes accident by jumping from high place, by aging, and some knee injured by sport activities such as football and badminton. There are three objectives of this project. Firstly is to redesign total knee replacement (TKR) of knee flexion implant from the previous design by using CATIA software. Secondly is to analyze finite element analysis using ANSYS software. And lastly is to analyze effect material to the performance in component of knee flexion using ANSYS software. There are three scopes of work of this project. Firstly, literature review. Secondly, design and analysis. And lastly is compare new design with original design. First, literature review is knee anatomy. The knee is the joint in which the upper and lower legs connect. The knee moves like a hinge and it is the biggest joint in the body that enables you to sit, squat, walk and jump. There are three bones in the knee: femur, tibia and patella. The thick or higher leg bone is the femur. The front of the lower leg is tibia's bone. Finally, the patella is the triangular bone on the front of the knee over the other bones. Second literature review is knee flexion. Every movement in the human body involves a force operating. A flexion injury of the knee is when the knee unable to tighten or stretch the knee properly. The normal active movement range for a knee is 0 degree, it is an extension, and 140 degree is flexion. Flexion injury make the activity of the movement of knee is decreased. Last literature review is material properties. For femoral and tibia, there are three different materials that can be used, which are titanium alloy, cobalt chromium alloy, and stainless steel. For tibia inside and patella, material being used is ultra high molecular height weight polyethylene (UHMWP). The material with different characteristics need to be analyzed in order to find the best material for component. First first methodology in this project is benchmarking. Benchmarking is a method to find the greatest achievement. The process of improving performance is also a definition of benchmarking by recognizing the exceptional approach discovered within and outside industry. Therefore, the procedure and outcome of analysis by using ANSYS software are credible technique of benchmarking. This slide shows the flowchart of design from start until end of the project. The 3D model of the knee implant was developed using CATIA software and then imported into ANSYS software to perform the finite element analysis. The design features of the femoral component are shown in this slide. There are three different modifications for the femoral part. The characteristics of femoral design are: firstly, design for deep flexion and safe flexion of 0 degree, 90 degree, 135 degree, and 155 degree. Secondly, reducing wear by increasing area of contact and distributing the stress more evenly. The design features of the tibia insert and polyethylene component as shown in this slide. There are three different modifications for tibia insert. The modification is to resisting edge loading. The space accommodates a larger contact area on the loaded condyle and resist edge loading. Next is increased contact and conformity help to reduce contact stress. Tibia component has one modification only. The difference between the previous design and the new design is the presence of the slot which can tighten the tibia insert or polyethylene component. The modification design has four characteristics. They are: firstly, extended posterior condyle on the femoral component to facilitate tibio-femoral contact to support deep flexion up to 155 degree. Secondly, conforming geometry of the femoral component with its bearing allow minimal loss of contact area in deep flexion. Thirdly, proportional side specs on the femoral component provide additional stability and fit. And lastly, increase contact area and lower the contact stress. Table 1 in this slide shows several materials that have been used in the component. For femoral and tibia, there are three different types of material which are titanium alloy, cobalt chromium alloy, and stainless steel. The material used for the tibia insert and patella is ultra high molecular weight polyethylene UHMWP. Material with different characteristics need to be analyzed in order to find the best material for the component. For this section, finite element analysis was run by placing the list features into the mechanical system. The geometry are imported from the design modification, which consists of three component modification, which are the femoral, tibia insert, and tibia. It is made by using CATIA software, in which the final product file is converted as a .stp file. The contact region between the tibia insert and the femoral component was determined as the critical connection. The meshing process was manually assigned to this assembly. Meshing analysis has the effect of increasing design precision, convergence, accuracy, and simulation speed. In this project, the knee flexion has four angles that need to be analyzed. It is 0 degrees standing, 90 degrees kneeling, 135 degrees squat, and 155 degrees sitting on the feet. Table 2 shows the condition of angle flexion. The example that need this angle is when Muslim prayer. All movement and activities during Muslim prayer use the angle of flexion that need to be analyzed. The patient weight is assumed to be 80 kg. For the knee implant model of all the design, titanium alloy was used as the material selection. The three designs will be benchmarked and compared to obtain the best design for the knee implant. The design will be evaluated in terms of their total deformation, equivalent stress, shear stress, and contact tool pressure. According to Table 2, total deformation of modification 1 is shown to have the least amount of deformation at all angles of flexion, except at 135 degrees. However, it only shows a slight difference with the value of modification 3. From table 3, which focus on equivalent stress, modification 1 shows the least amount of equivalent stress at all angles of flexion. Next, table 4 depicts the result of shear stress. The value of 0 degrees of flexion angle for modification 1 was the highest compared to the other modification. The value at 135 degrees is slightly similar to the original design. For 90 and 155 degree, modification 1 have a less shear stress than others. Based on the table contact tool pressure, modification 1 has the lowest amount of contact pressure at all angles of flexion except at 135 degrees, which modification 2 has the least contact tool pressure. The chart shows the difference between modification 1 and the original design. The highest contact pressure is at 155 degrees of flexion. The graph also demonstrates how increasing the angle of flexion can cause an increase in contact tool pressure. From all the table and the chart, it can be concluded that modification 1 is the best design because it has the lowest value of total deformation, equivalent stress, shear stress, and contact tool pressure. This slide shows the total deformation from modification 1 design with different material. The table shows titanium alloy and stainless steel has the slightly different value of total deformation. However, stainless steel is less deformed than other materials. Next, this slide shows the equivalent stress from modification 1 design. The table also shows the slightly difference between titanium alloy and stainless steel. The titanium alloy is less stressed than other material. This slide shows the shear stress from modification 1 design. The titanium alloy is less shear stress than the other material, but at 90 degrees, cobalt chromium alloy is less stressed than other material. From this slide, stainless steel has less contact tool pressure than others design except at 90 degrees. Ideally, the lesser the amount of deformation, the more suitable it can be used as the chosen biomaterial. Through observation, stainless steel has less deformed than others. For equivalent stress and shear stress, titanium alloy is less stressed than others material. It can be seen that under all the equivalent stress and mostly in shear stress, titanium alloy in all angle of flexion has a lesser amount of stress. The material of stainless steel, on the other hand, show less pressure. In conclusion, titanium alloy is preferable to stainless steel when biocompatibility is considered. Titanium also has better corrosive resistance than stainless steel and can endure it for a longer period of time. In the nutshell, the objective of this project are to redesign total knee replacement TKR of the knee flexion implant was done by using CATIA software. Finite element analysis was done using ANSYS software. And finally, an analysis of the effect of the material on the performance of the component of knee flexion is clarified. The improvement of the knee implant in this final year project contains 3 alternative designs based on previous design. According to the finding and discussion, modification 1 improved total deformation, equivalent stress, shear stress, and contact tool pressure at all flexion degrees. Angle flexion at 155 degrees is a critical component of the design. The modification of the knee implant is important to take into consideration of the magnitude of the load at the knee during treatment of the patient that commonly perform deep flexion during activities of their daily life. In addition, the best material of knee implant is titanium alloy for femoral and tibia and ultra-high molecular weight polyethylene for tibia insert and patella. That is all for my presentation. If there are any question or comment, you can contact me through my phone number or email as displayed here. Thank you for watching.